Welcome to the NPTEL course on fractals and multifractals. So, in this lecture series, we are discussing the Hausdorff metric and its property. Previously, we have defined and see some of the examples of Hausdorff metric space and their examples. In this lecture, we will discuss how to find the Hausdorff distance of two closed interval in the real line. Let A and B be a closed bounded interval in R. We will take A and B be a closed bounded interval in R. Then the definition of the Hausdorff metric or Hausdorff distance is given by the maximum of distance between A and B and distance between B and A. Then this can be distance between A and B can be written as here, and the distance between B and A is written as here. Now, we are taking that A and B is a closed and bounded interval in R. We are taking the usual matrix R with usual metric. So, instead of D, one can write the modulus, the standard Euclidean matrix. Then, now, first one need to complete distance between A and B. Then we will move on to finding the distance between B and A. For computing the first term for this one, supremum infimum of x minus y, first one can fix for x belongs to A comma B, we need to fix one element in A. We need to fix one element in A. Then the nearest point in B is there are following possibility. If we have the two interval like this one and this one, I am just writing here, this is A to B and C to D. This is my set A and this is my set B. So, for finding the distance between A and B, first one can take one element in A. We have to take one element in A here, x belongs to A. Then the nearest point in B we need to find. The nearest point is first fix the A, the fixing A, find the infimum of y belongs to B such that the distance between x minus y we need to find. So, we need to find the nearest point in B. Now, for this x there are three possibilities. If this x is less than the c, the lower bound of this interval, if x is less than the c, that means x is here, then the nearest point is c minus x is the nearest value. This is the nearest. If x is here, we are taking obviously both are disjoint sets, therefore, our x must be here. If our x is less than c, then the minimum distance between these 2 points is c minus x. Then other case, if x is inside this interval c and d, then the nearest point is 0, because the same point is belongs to the set c and d, therefore, the nearest distance is 0. If x is less than c, the nearest distance is c minus x. If x is lies between c and d, the nearest distance is 0. Suppose x is above this d, that means x is greater than d, that means here the nearest distance is x minus c. Here this is the largest number, so we need to count here x to d. Then we have three possibilities. Then we need to take infimum of nearest distance and they need to take the supremum. There are three finite numbers, therefore, we can take the maximum of c minus x, because worst possible case is c minus a. C minus D, because we are taking, if you are taking this is C and this is D, if my x is here and this is my A and B, then the nearest point is x minus C, the nearest point is x minus D, then the maximum we can take as A minus C. So, C minus A, B minus D, and 0 is the possible maximum, because we need to take the supremum, among all the infimum, then we need to take the supremum. Then from this one, these three things we need to take the maximum number. Similarly, now we are finding the distance between A and B. This term is over. Now we need to compute the this term, supremum infimum of y minus x, distance between B comma A. Or before that, for A, x belongs to A comma B, the nearest point in B can be written as in the form of function infimum of x minus y has this three form, and supremum infimum of x minus y we can write in this form. Now similarly, the supremum and infimum of y minus x, that means the distance between A comma B can be written as A minus C, D minus B and 0. With the similar argument, one can get this one. Now the Hausdorff distance is of closed interval A, B and C comma D is obtained by taking the maximum of these two, but here the maximum falls under the same number. Therefore, HD of A comma B equals maximum of, you can take the modulus of A minus C and modulus of B minus D, this number we can ignore. So, the Hausdorff distance between AB and AB, which is equal to maximum of distance between A and C and B and D. Suppose we have the two sets like here, A is here and B is here. Assume that if both are disjoint sets, here C and here D, then the distance we need to find, A to C we need to find and B to D we need to find. Among these two we need to take the maximum one. Suppose sets are like this one, overlapping set, here A to B, here C to D. Now you can see the A to C we need to calculate the distance and B to D we need to calculate the distance. Then it will give the how much, though it is overlapping set, that means both the set having the common points, then this distance never be 0, will get the some positive number. If you are taking this one, this never be equal to 0. And one is both are disjoint, yes, both are disjoint, some overlapping set. If both are equal, if the both the set A and B are equal, then A equal to B, A equal to C and B equal to D, then we will get 0, A to C and B to D. Yes, perfect. Now let us find the distance between the interval 0 comma 1 and the interval 5 comma 6, 5 comma 7 maybe. For finding this one, now our A is 0 to 5, we need to find the distance and we need to find the 1 to 6. So, 0 to 5 the distance is 5 and 1 to 7 the distance is 6. So, we need to take the maximum among these two number. Therefore, the Hausdorff distance between the interval 0 comma 1 and closed interval 5 comma 7, which is equal to 6. 0 comma 1 and 5 comma 7, we need to find the lower bound to lower bound and upper bound to upper bound, then we will get the 6. So, in this way we can find the Hausdorff distance of two closed between two closed interval. In this way, we can find the Hausdorff distance between two interval, closed interval, especially in the real numbers. Thank you.